Sir, please unmute your mic.
Oh, sorry, I was speaking without the mic. Okay. Okay. So yesterday we discussed a circuit with a transistor, okay, with three resistances. This RC, RE, emitter resistance, and a base resistance also. Okay, RB. Okay, and I'm giving a supply VCC plus VCC. Okay, now we had already discussed this circuit has an inbuilt feedback mechanism. Okay, so when the IC is increases, there is a inbuilt feedback mechanism which will reduce the IC automatically. When IC is changing with respect to temperature or any external conditions, what happens? The Q point is going to shift. When the Q point is going to shift, your output voltage swing is going to get affected, and you may get clipped. The output signal may get clipped, and a lot of noises can happen. Okay, so we want to avoid that. So one thing is we can perfectly bias it. Uh, so still there is a problem of beta dependency. So by biasing, we can eliminate the beta dependency also. Okay, because beta is varying with respect to temperature as well as IC also. Okay, so this is one circuit which has the inbuilt feedback mechanism. The feedback concept is very important. What is the feedback concept? Feedback, any system we have studied, we have an input and output. There's some system inside the system, there's some process going on, maybe mathematical operation or some hardware or some software, whatever. So that system, if my output is given back to input for some stabilizing or some kind of monitoring mechanism, so there we tells it is a concept of feedback. Okay, we're giving some part of the output back to input for maybe stabilizing, maybe error monitoring, error reduction, okay, gain stabilization, what also any reason I'm taking some part of the output and giving back to input. That is called feedback. Okay. Here, why feedback is used? Feedback is very important because one of the entire different field of system or what we call mm, one entire different field is the control system. So this one of the field where we design automatic systems, automated systems which can stabilize themselves, which can monitor their own output and stabilize. So we have different controllers. So this is one of the concept we are taken from there. We are getting some part of output and using it to maintain the stability of the system. Okay, here we are taking some part of the output voltage or current, and we are monitoring the rate, the increase of that quantity, maybe I see here, and based on my output, I'm again trying to give the signal back to the input so that I can stabilize the input parameters so that my IC is maintained. If IC is going too high, automatically the output will sense some parameters is going to sense it and giving back to input that okay, decrease this thing, decrease IB. So I'll decrease IB. Again, the IC is decreased. IC is again decreased. Again, there is some mechanism in the output voltage or current signal which is going back to the input and telling okay, you just increase the IB so that IC is also increased. So some way or the other, the IC is maintained through a feedback mechanism. So this concept is very important. We'll be using it especially in the last module, op amp, etc. So so I just want you to see the circuit and think in your own mind how the feedback mechanism is working. 1 minute I'll give you, think yourself, and make sure you got the concept of feedback. Okay, Are you able to visualize the concept of feedback? Okay, so let's see how the feedback works. Okay, here we know RC is connected to collector of the transistor, so current passing through this resistance we call IC. Okay, so this IC is the current passing through RC and coming through the collector of the transistor. Okay, so ultimately our Q point is fixed, fully dependent on the function or a function of IC. So what happens sometimes because of temperature variation or beta variation, IC may increase. Okay, so what happens here when IC increases, what is going to happen here? So first we have to write the Kirchhoff law here. What is the Kirchhoff law? VCC equal to VCC supply voltage is dropped across ICRC plus VCE plus IERE, or we can say IERE or IC and IE are both same for all practical purposes. So I can make I equal to IC also, not a problem. Okay, so this is the Kirchhoff law. Input supply voltage VCC is dropped across ICRC, VCE, and IERE. Okay, and the input part or the equation in the input part, I'll write the equation again. VCC equal to input supply voltage will drop across IB into RB, IB into RB plus VBE, base emitter voltage, plus same IERE, IERE. Okay, so these are the two equations what we have now. Some because of some reason IC is going to increase. Okay, so what is happening if IC is going to increase? Which all parameters here is going to increase here? Definitely IC is increasing. The voltage across RC is going to increase definitely, and voltage across RE is also going to increase, right? Voltage across RE. What is the voltage of RE? VE or VRE. I call VRE. VRE is going to increase definitely. So you can see the VRE is connected to both input and output circuit, output part of the circuit. In both equations, I have VRE. This is nothing but IRE here in the input equation, output equation also we have IRE. So what happens when VRE is going to increase? If IC is increasing, voltage drop across RE is increasing. That is nothing but VRE is going to increase. So from come back to the equation of the input circuit, when VRE is going to increase, what is going to happen? VRE is going to increase. That means IRE is increasing. We can see the other parts of the equation. You know, VB is constant. VB is a constant for silicon and Germany, whatever. So what the only value which can decrease is IBRB has to decrease. Why? Definitely because VCC is a constant. VCC is a constant. VB is a constant. So as IERE increases, correspondingly IBRB has to decrease. So what is the meaning of IBRB decreasing? IBRB decreasing means voltage across resistor RB has to decrease. The voltage across resistor B, we call IBRB. VRB decreasing means what? RB is constant, so definitely IB has to decrease. So net effect is my IB is automatically decreased. So you know when IB is decreasing, definitely IC is also decreasing. So what is this is the after effect of increase in IC in the output circuit. So the increase in IC in the output circuit is reflected back to the input, and correspondingly IB is automatically decreased to maintain the IC value, or IC is then decreased because of IB is decreasing. Okay, so this concept is called a feedback system. The same thing happens when IC is decreasing. Initially, if IC is decreasing because of any reason, what happens? The voltage VRE is automatically decreased. When VRE is decreased automatically, we know input circuit IB, RB, the voltage across RB resistance is going to increase, must increase. Why? Because VB and VCC is constant. So definitely IB, RB or voltage drop across RB has to increase. So what is the meaning of VRB increasing? Nothing but IB has to increase. Okay. So when IB is increasing, definitely IC is also increase because it's a linear relationship. Okay. So this is the feedback mechanism. Uh, okay. So this biasing is called base emitter biasing. Base emitter biasing. Okay, so that something which we are refreshing from last class. Now I will ask some of the techniques and you have to tell me uh, the circuit is beta dependent or beta independent. Okay, so I'm going to draw some circuit and You have to tell me whether these are beta dependent or beta independent. Okay. Let's start with base bias circuit. Okay, we already discussed base bias. So I think this class we should end the biasing part and we'll go to amplifier part. In the after this portion, we'll go to amplifier. Okay. So the first circuit is the very common thing which you have studied initially. The base resistance. This is transistors, and this is the resistor, and there's a VCC given, and there's definitely I need a VBB given, VBB to be given in the input. Okay, and this is the grounded. Meter is grounded without anything. Okay, so here I have two transistors, RC and RB only. RC and RB only. So this bias type of biasing is called base bias. Base bias. Okay, we have base resistance and a voltage source in the base. Now, tell me, is this circuit uh, beta independent or beta dependent? And what are the plus and what are the minus of the circuit? You can type in the chat so that I can read. Is beta dependent or beta independent? Is this good circuit? What are the advantages? What are the disadvantages? What are the characteristics or where can be used, etc. Something. Don't comment us on this. Yes, is this beta independent or dependent? Yes, I'm not getting any reply.
So beta is dependent only temperature to.
Yes, can you repeat?
So beta dependent only temperature, not
What
any.
beta temperature? I'm asking. Yeah, can you repeat? I'm not able to get what you're saying. Beta dependent or independent?
Sir, not dependent. Sir, beta is constant.
Yeah, beta is constant. Beta is constant, but that is the whole point of last lecture. Beta
Yeah,
is
sir.
constant, but it can vary. In a fixed temperature, it may be constant,
Yeah, sir.
but still it can vary. It can vary based on temperature, or it can vary based on IC also.
Yeah, yeah.
It can vary. I'm not telling that in a particular circuit we can take beta as constant. With a fixed circuit, we are designing the all the resistance, everything, and fixed temperature, pressure, environmental condition. We can assume beta is constant. But in rare situations and based on temperature, definitely beta may vary. So to avoid that variation, we are designing circuit so that circuit is independent of beta. My question is this circuit or the biasing of this circuit, the Q point of this circuit is dependent on beta or independent of beta? Even if beta is constant, leave it. Even if you can assume that beta is constant, but still it's our designer's duty to make sure that circuit is the parameter, the Q point of the circuit is not directly depending on beta. That means no point while calculating the Q point, VCE and IC, I'm using beta. So are you able to get? I think only I'm getting one answer and two answers. Yeah, two answers. Yeah, this circuit is actually beta independent. Why? Let's calculate Q point. When you calculate Q point, you get that there is no dependency of beta in those equations while
Yes,
calculating IC and
yes, sir.
VC. Okay, so this is a beta dependent. Why? If you calculate IB, you can calculate IB first. How we calculate the biasing point here? Yes, first take the input circuit. Okay, input VBB. VBB is drop across RB and VB. So
VB,
IBRB, yes, IBRB plus VB. Okay,
VB, yes.
what we'll get from this equation, we'll get IB. We get IB from the input circuit, that is VBB minus VBE divided by RB. That is the first part. Once you get IB, then you calculate IC. This only way is IC equal to beta times
Beta.
IB.
Beta IB.
So you're right, because beta here is fine. Beta is constant only here, but still we should know that the Q point is still dependent on beta. Okay, so IC is, there is no other way of calculating IC other than the beta thing. So IC equal to beta times IB. Now VCE, we know VCE equal to, VC is VCC minus IC into RC. Okay, that is VCE. Now this is C, this is E. Okay, so this equation I can see easily. I can find that this is a beta dependent circuit because my IC is definitely depending on beta. Okay, so this circuit I can say is beta dependent, but this have few parts. It is very simple. You can see looking base circuit have a simple, collector circuit also is simple. So it is simple circuit, but it is beta dependent. So but it's one of the disadvantages. I'm using two supply voltages, right? You can see that's one disadvantage. I'm using VCC as well as VBB. In a practical case, it may become a bit difficult to have a different voltages in base and collector. Okay, and we are using two resistances also. That is okay. But at least, so this type of circuits are mainly used in digital switching. Okay, digital switching where I have an input 1 and 0. You remember we have a switch AND gate, OR gate, NOT gate, etc. Okay, if I give a high base, your output will be 0. If you get 0 in the base, output will be high, something like that. Okay, so this kind of digital switching can be applied. So now next circuit I'm going to draw is, okay, I have VCC and now a RC, then I'm a transistor, and I have RE also, and now I have a voltage VBB, the base voltage, plus minus whatever you can say, and we have RC and RE. RC and RE. Now tell me, take some time and tell me whether this circuit is beta independent or beta dependent. The only thing you have to think is, you have to see when you're calculating IC and VCE, think whether you are using beta or not. That's the only thing. In mind also you can see. Yeah, this circuit is beta. I'm getting only answer from Pradeep. I don't know whether others are not able to understand or so. What about Rajnish? What is your opinion on the circuit?
Sir, sir, I'm not clear this circuit.
Okay, so you got now what we have to do. We have to calculate the VCE and IC. We have to
Yeah,
try
sir,
to
I
calculate
know.
VCE and okay. So you can take your time. So let's see. Let's go ahead how to calculate. So first thing you have to do is you don't have any base resistance here, right? You don't have any base resistance here. So only
Yeah, sir.
voltage here given to VBB. Okay. So light
Yeah.
Kirchhoff, we'll try to draw Kirchhoff law here. VBB has to be a drop across. This is plus minus. VB is plus minus. Drop VB has to be drop across. So we can say VBB plus VBB plus VBB and minus VBE. Again, same voltage has drop across RE also. That means VRE. Okay, VRE equal to 0 according to Kirchhoff law. So from here, what we'll get here, we can get that IE. VRE have two things. So for example, again simplify VBB minus VBE. What is VRE? IE RE. IE equal to 0. Okay. So now I have IE. Now I can calculate IE. So IE is very simple here. IE equal to VBB minus VBE divided by RE. Right? Now
That's
once we got IE, we know IC is approximately equal to, we know this IC approximately equal to I for all practical purposes. Maybe we are tolerating error of 1% something. Then we got IC. We can directly see that we are directly getting IC without using any beta. Okay. Now once we got IC, we know how to calculate VCE. You know VCE. What is VCE? This is collector. This is emitter. Okay. So voltage across those 2 points. How we calculate? Yeah, Kirchhoff law in the output circuit.
Output circuit, yes.
Yeah, VCC equal to ICRC plus VCE plus IRE or ICR. I'm just writing ICRE because
Minus
anyway, no,
minus
I'm
R.
just writing. I'm writing equal to here. Okay, I'm just
Yes,
writing
yes,
equal to here. VCC equal to. VCC equal to. That means input source is drop across RC, RE, and VCE. Okay. Now from
yes.
here we can calculate the value of VCE. Okay. So VCE equal to VCC minus ICRC minus ICRE. Okay.
Yes, sir.
So whatever we can got VCE, but here beta. Okay. So just seeing this base circuit also we can understand whether the circuit is beta dependent or independent. Okay. So this is one way. Now I'm going to write and draw another circuit. So this circuit is definitely this is beta independent. Okay. This biasing was emitter biasing. You can see there is no base bias, but definitely emitter bias, which we discussed yesterday. The base resistance is gone to plus some question. So if RB is present, then it is beta independent. It is right or wrong? No, we cannot say like that. We cannot tell that if there is some RB, it is beta dependent. If there is no RB, it is beta independent. No, we cannot tell like that. We'll see one example where there is some RB and still it is beta independent. Let's see. Okay, so next example. So here it is clear we are not using any RB resistance, and this RB is coming to RE. This resistance is coming to RE. So it's called emitter bias. Now we'll see some circuit with some RE. Some RE. That is we have already discussed. Here transistor. Now the RC. Writing RE also. Now I need to put some base bias. So I'm giving some kind of RB also. Okay. So this is called voltage divider bias. Voltage divider bias. Okay. So here also these resistors are usually named as R1 and R2, and it acts as some kind of base resistance only, because when we discuss the amplifier part, we'll discuss the AC analysis. In AC analysis, this R1 and R2 becomes parallel, and we'll calculate RB base resistance by R1 parallel R2. That is maybe next class or tomorrow. So we'll leave it. Okay. Now, what about this circuit? Now, question is this circuit beta independent or beta dependent? So RC, this is depend on beta. This is an RE. I'll get some answers, but how can like we have discussed how to calculate this circuit. We have discussed how to calculate this. How we calculate? Let's start with yes. We need to start this circuit, right? This bottom part circuit will give us the current in the uh, across the emitter RE resistance. So first we have to calculate the base voltage like any other previous questions. First we are calculating the base voltage, and if possible if there is a current there, we'll calculate the current, then calculate the collector current. Because if beta is not given, then IB is going to be 0. No, beta is not given doesn't make anything. Beta is not given means beta is not given. That means IC can IB cannot be 0. If IB is 0, transistor is off. Yeah, you're right. Transistor is off when IB is 0. But if beta is not given, doesn't mean there is no beta. Beta is not given means doesn't mean beta is 0, right? Okay. So if some circuit is independent of beta, beta will not be given to you. Why? There is no need for beta. Because that is the advantage, right? If beta is, my circuit is beta independent, that means my Q point is more stable. It's not going to vary with respect to variation in beta also. Okay. Why? Because beta can be dependent on temperature. Yesterday we have seen a graph. I hope that you are plotting this graph in your notebooks. Hope that you are plotting this graph, and these are very important graphs. That indicates that beta can also vary. Although for all practical purposes we'll take beta as a constant, but in reality, in practical scenario, we see that beta is varying according to temperature, IC, pressure, humidity, etc. maybe, and that is given by the data sheets of the transistor. Okay, so here the first thing we have to do is we start with the base part. So first we calculate the base voltage VB here. VB. What is VB here? We can see that VB is actually voltage divider. That is nothing but VCC into R2 divided by R1 plus R2. Okay. So we got, according to Thevenin's, we got some voltage here, and that is VB. We got the VB here. So once we got VB, we'll proceed exactly like we have proceeded in base bias, sorry, emitter bias circuit. How? Yes. Right now, after getting VB, we know VB is dropped across VBE and VRE, right? Okay, and we know VRE is nothing but IE into RE. Okay, we IE into RE. Now we can see, we can directly calculate IE from this equation. So I calculate IE is nothing but VB minus VBE divided by RE. Okay, we divide by RE. So here also we can see that IC, we got IE without use of IB or beta. There's no beta independent equation also. This is also beta independent equation. So once you got IE, I already have discussed, we can take IC approximately equal to IE. Okay. Now we can easily calculate the VCE also from the Kirchhoff law in the output circuit. VCC equal to ICRC plus VCE plus IERE. Okay, phi C is equal to IE. I can say that. Then here also VCE equal to VCC minus ICRC minus ICRE or IERE, whatever. So we got VCE. So we got VCE and IC without using beta. This is the main thing. Okay, we got IC or IE and VCE without using beta at all. So I'll tell that this circuit is beta independent. Okay, so this biasing is called voltage divider bias. One of the advantages of voltage divider bias compared to other biases we have discussed right now is we are using only one voltage source here. So we can say this a bit simpler and it's independent of beta, and mostly this application is using as a amplifier. Okay. Now maybe we'll discuss one more circuit which is usually seen or coming in the exam. That is what I can say. So one circuit is, I'm drawing circuit. You have to find the Q point. Okay. So the transistor. So RC. Definitely there is a RE and grounded. There's a VCC. And definitely there is a resistance. And we are grounding this also. Okay. I'm changing the ground of this emitter part. Instead of that ground, I'm putting some voltage here. And this voltage I call VEE. Okay. Now I'll give you the value of this voltages. This is 10 VCC is 10 volt. Okay, and ground is 0 volt definitely. And VEE is also I'm giving -2 volt. -2 volt. Okay, so I'm given all sources. Now I'll give you the values. RC is equal to 3.6 kilo ohm. This is RC. This is RE, and this is RB. Values 3.6 kilo ohm for RC, and RE equal to, we can take 1 kilo ohm, and RB 2.7 kilo ohm. Now you have to calculate the Q point. Q point means IC, yeah, IE and VCE. It's interesting that the base is grounded. Although the base is grounded, still the transistor is in active region. Active region means it is operating. The base emitter junction is forward bias, and collector base junction is reverse bias. Still, it is maintaining that forward bias by a negative bias in the VEE. You can see that I'm putting VEE as -2 volt. It's not VE 2 volt. It is -2 volt. Okay. Then only my emitter base junction is forward bias, right? You can see the emitter base junction. What is this? Is N, P, N transistor. So the P region is what voltage is P region? Yes, it is 0 volt. What is the voltage at the N region? Yes, it is -2 volt. So it is forward bias, right? P region is higher potential than N region. N region is -2, P region is 0. So 0 is much 2 volt greater than -2. So definitely it is forward bias. Okay, so how you start calculating? As usual, we have to start with base circuit. We'll write the equation in the base circuit. Where the voltage given 0, then that voltage should be dropped across IB, RB, and VB. Definitely VB. There should be voltage at VB, and there should be a voltage in the RE also, RE drop also. I think I want everyone to draw the circuit in your notebook. Okay, draw the circuit in notebook and try how to solve this. And I want everyone to remember that we are still in the DC biasing. We are not thinking till now of giving a small AC signal and getting it amplified. Right now, we are trying to prepare the transistor to ready to amplify some signal. Okay, so we are still in the preparation mode also. Preparation mode only. Next, we will go for transistor, and then we'll give some input. Okay, so I'm just trying to calculate this circuit. So where will we start? Let's start. Okay, so first I have a base circuit 0 volt. So I'll write the Kirchhoff law in the base part. So I'll write 0 volt plus, again the current is flowing. So this is plus and this is minus. So minus IB minus IBRB, right? So IB RB. I don't know what is IB till now. And then we have plus minus, again VB minus VB VBE, again minus IE RE. Okay, I think this is clear. This is equation clear, and see what equal to 0. Yeah, there is equal to 0 definitely. Equal to 0 is, yeah. Any doubt? This is I'm writing Kirchhoff law in the base part. There's a voltage source 0. I take it. Okay, there is not equal to 0, equal to -2. Yeah, equal to -2 volt. Right. Because V is -2. So what I'm doing, I'm trying to write the Kirchhoff law in the input loop. This is the loop, input loop. You can see there's a two voltage sources, one is 0, one is -2. I'm starting with 0 volt, 0. Okay, let's once, we'll write once again. Think we missed something. Let's write once again. Here also is, it should be very clear that if you write the right Kirchhoff law, you should get the answer. So don't need to worry, no need to think much. You just write the Kirchhoff law. Now I'm going to write again the Kirchhoff law. Okay, so this is 0 volt. Then VE is minus. So I'm going to draw this voltage minus plus this is the voltage, and again this is 100 0 volt. Okay, fine. Is it clear right now? I just connected the base circuit. Now we can so that we can easily write the Kirchhoff law. So starting with 0 volt, I'm starting from 0 volt 0. Whatever I didn't care whether 0 is plus or minus whatever. So 0 volt, then plus or minus. Current flow is like this, so it will be plus or minus. Then so minus IB RB. Again VB should be minus. This is plus. P is plus. N is minus. Again minus VBE. Okay. Again there is a current flow from top of the resistance RE to the bottom of the resistance. So again minus IE RE. Again now voltage source I'm seeing the minus starting, then minus to plus, again plus, plus 2, that is plus VE equal to 0. Getting? If this is clear, I think it is half done. Now we can see what all things are given. RB is given, VB we know, RE is given, right? So what all things are missing? IB is missing and IE is missing. So what is the next step? I think we can directly write another Kirchhoff law if we don't need to use the IB/RB thing. One thing I can see from here is the input, the P of the base of the transistor is already getting what voltage? It's getting them 0 volt because I'm given 0 volt. So here another possibility right now we can substitute for IB. Okay, right now we have two unknown variables, IB and IE. So if I assume IE as IC, right? What I'm doing here, I'm trying to see this IE as IC because this is approximately equal. I can take it always equal. Then I substitute IC as beta times IB. Okay. Then I can reduce this single equation of two unknown variables into single variable of IB. Then you may ask like, what is the beta then? Then yeah, I should give beta also. Beta also. Yes. I should have given beta also. Okay. So when I give you beta, you can easily calculate the IB from this equation, right? Okay. So from this equation, the unknown is IB and beta. So we can, even if some question beta is not given, what should you do? You should take an approximate value of beta. You can write that assuming beta equal to 200, or assuming beta equal to 150, assuming beta equal to 250 or 300 is also fine. But so that you should not get stuck anywhere. You should just take assuming beta is so much and you should continue. If in the exam you're getting stuck or somewhere, you can take it for all practical purposes. Unless some other value beta is not given, you're not able to move forward, you just assume something, because these things are practical things. We have to do this practically. Okay. In many of the practical things, what we do, we take the download the data sheet and see what is the value of beta in this transistor. We go ahead with that thing. But in exam, you don't have any options of referring to data sheets. Although in lab exam there is definitely option of referring data sheets, but in theory exam you can go ahead with a good value. Good value. You should not take beta equal to 1000, which is not assumption, or beta equal to 1 2 3 or something. So practical value you can take anything, you can value any value from 100 to 300 or something. Okay, so then in this equation you will substitute everything, you'll get the value of IB. Okay, now once you get the IB, here also again you can assume, you know, beta is given, so IC you can calculate beta in, because everything is given, RC is given, RE is given, so you can find the voltages. So one uh, another way of doing the same circuit is, so VCC. It's not ground, sorry. It's VEE. VEE. See. Okay. Now this is minus 2 volt. This minus 2, and this is plus 10. Plus 10. Another way of analyzing the circuit, can I assume that the 0 volt is coming across the base here? 0 volt. Because I given 0, this is coming across 0 volt. Can I take like that? It's a question. The things are very much simplified. Then, you know, plus minus, there's a base voltage VB, VB base voltage, VBE. Then other voltage is RE, VE, that is VE. What I can say, 0 minus 0.7, I'll get what? VE. And now what is VE? No, this is not right. 0, 0 plus VB. I'll just write VB. 0 minus VBE. VBE. Then we have VEE. We have IERE also. Minus IERE minus or plus 2. Plus 2 equal to 0. No, I think this assumption, 0 volt assumption, is not, can be valid only if IB equal to 0. And IB cannot be equal to 0 here. There should be some IB. Okay, so you leave this analysis. I think this is one of the analysis given in Malvino. So maybe we'll refer to it again. But I hope in circuit IB there should be some IB, because although the base is 0 volt, but the VEE emitter is always minus 2 volt. Emitter VEE is always given minus 2. So there will be some current from this base to the emitter region. So we cannot take as base VB as 0 volt. Maybe. Okay. So leave it. You can follow the first way of analysis. Okay. Where we have taken IB, RB, VBE, IERE, and VE, all these 2 voltage source, and we just substitute for IB. Even if your beta is not given, I can assume a value of beta, and you can continue in first what we have done in first case. Okay. So the main point is there can be multiple ways of doing the same problem. So you have to try using your basic fundamentals like KVL, KCL, okay, all those things. Okay. So we can refer to Malvino also. So Malvino, there are a lot of problems given, and this type of analysis is also given in the Malvino. And Malvino is the best simple book available. You can refer to it. and can do a lot of problems also from there. Okay, so now I'm giving you another circuit. Now we have already imagine we have already biased. The transistor is already done. We are done with the biasing. Now uh, all the Q point thing we are fixed. Okay. Now what is the next step? Next step is you have to give a AC. Okay. So how to give an AC? Now the DC part is fixed. Now transistor having a fixed IC, VC, everything is done. Now I have to slightly change the base voltage. We have to give input to the base part of the amplifier. Okay, so how I'll give the base part? Everything is BC, everything is DC right now. So if we give an AC, it should not get affect the biasing point. So what I'll use a capacitor here. Very important. I use a capacitor because I know capacitor have a low impedance to AC. So I give a small capacitance before giving my input AC signal. So this is my AC signal. Okay, so AC signal is going through a coupling. This capacitor called coupling capacitor, CC, coupling capacitor. So there are two voltages. One is DC here and AC here. So AC and DC should not get mixed together. Okay. Okay. So what I'm using a small capacitor. Why? Because capacitor is required because the DC signal should not go to my source. Right? What happens? So I don't use a capacitor. This DC voltage can affect the source, well, the signal source. That is maybe microphone, that may be a sensor, gyroscope, a small micro sensor, a pressure sensor, whatever. It can be any type of micro sensors which is giving a signal in microvolt or nanovolt. So this DC should not affect my source also. Okay, so you say capacitor. It's called coupling capacitor. Okay, so this coupling capacitor allows gives zero impedance to AC to come into the input of the amplifier, but it gives infinite impedance to the DC. Okay, you should remember that capacitor is offering infinite impedance to the DC. Why? Because the DC frequency is, XC, impedance of capacitor, just XC equal to 1 by C omega, right? 1 by C omega. So the frequency, the higher the frequency, capacitor offers less impedance. So for AC, capacitor offers much less impedance than DC. Okay. Now, so this input is right now going to the base, and possibly we get the amplified output in the output of the where the output of the transistor in the collector part. Okay. So we have to collect the output from here. Again, I use capacitor here. This is another coupling capacitor. This is another coupling capacitor here. Output coupling capacitor to collect the output voltage. Okay. So again, I'll write the name here. CC. This is another coupling capacitor. CC, output coupling capacitor. Okay. So that the DC is not affecting my output. For example, I have another device in the output. For example, I have another device. Maybe there's some kind of signaling device, loudspeaker or something. Okay. Was I have loudspeaker where I have a lot of sound. So this this DC, biasing part should not affect my output part of the circuit. So I use a coupling capacitor here also. Okay. Now what is happening? Now the input is coming. The input is coming to the base, and the slight variation IB is coming. Delta IB I call delta IB. Now with the IB, I'm using a small letter I, small letter B. Why? Because right now I'm referring to AC. Okay. So this small change in IB get a greater change in IC here. Okay. Then the voltage of delta VC, small letter VC also is very high, and I get amplified voltage in the output. Okay. So that's it. So rest amplifier modeling will continue tomorrow. So that's it. So we'll make some models of AC models of transistor. Then we see what is amplifier. We calculate input and output resistance of amplifier, and see what is the gain. What is the gain? How much amplification we are going to get, etc. etc. I will discuss tomorrow. Okay, so we can stop the recording, and you can, if any doubts, you can ask, or